All right, so now we dive into logarithmic functions and one very big important kind of formula, or I don't want to call it a formula. I guess I would call it an identity. And that identity being how we transform from exponentials to logarithms. So in these first six questions, what I'm gonna try to say is, especially in these like first two, is I kind of want to say that these are things that after we look at what we're saying here, you should be able to look at these first two and kind of know that they're true and understand what they're saying. And even like number six looks a little funky. And number four, catch this, number four is a direct result of what we talked about here in this first section. So what's going to become super, super important that you know is that negative exponents transfer to the bottom and turn positive. Also, you're going to need to eventually remember that square roots are fraction exponents, or any type of root is a fraction exponent. Now, that means an exponent in the fraction. So notice the difference here. This was a negative exponent, so it introduced a fraction with positives on the bottom. This was, again, a negative exponent, but now there's a fraction with a positive exponent on the bottom. Now, what I'm saying is a square root, as we'll see here, is a fraction as an exponent, and so we'll see what goes on there. Anyways, so the question is, do you know your bay? And that's just a dumb joke, and this goes back, I don't know, gosh, what, to 2016? No one says bay anymore, but I do, because I'm a mathematician. So here's formula number one. When we write log in mathematics, what we're saying is that because of the way this is written with a log, we're saying that some number was raised to some exponent, and after that was done, we got this. So that's why I say, I used to say log is bay, because a log has a base, which was raised to an exponent, and it gave me an answer. So there's a base, I know the answer, and the question that a log answers, don't miss this, we could almost say this. A log determines the exponent of a base. So what am I saying there is that this is saying that if let's even look at this and cover this up. The way that we're going to read this now, according to what I'm saying to you, is that there is a number 8 that was raised to some power, and it got me 512. So notice what I mean by like bay, and BAE. I mean what the asterisk, or not asterisk, acronym is base answer exponent. So my base is 8. It was raised to some power and got me, aka gave me an answer of 512. And the question then is, what is the exponent? And here it's just written out. The exponent must have been 3. Well, so then how do we translate that into maybe more familiar wording? Well, the answer is that there was a base that was raised to an exponent, and it gives you some sort of answer. And so these two go back and forth from one another. And notice that you don't have to write the E after to the right of the equal sign. It could go first, like we see in number 1. But it's more so about, again, the log has a base, there is an answer, and the other side of the equal sign, or what it determines, is the exponent. Or there's a number that can be raised to an exponent, and then the answer of that is something. So how do we back and forth through these? These actually go by really quick once you memorize this. Here we go. Well, like I said, there's a base of 8. The answer is 512. And 3 is the exponent that my base was raised to. And so really that's your verification right there, is what is, or how do you get 512 with a base of 8? The answer is you raise it to the exponent of 3. I can check my work by just saying what's 8 cubed? 512. Now, what we aren't too concerned about, sorry, I'm just trying to get rid of that glare. It's good enough. Never mind. There we go. All right. Where was I? Getting rid of glare. So there is a way on calculators to deal with logs. Your homework is going to say just do it yourself. But I'm going to scroll down to write log base, and I can see that if I type log base, 8 and then 512, notice how that 8 is a subscript, it's not multiplying, it spits out 3. So you can see my calculator is doing fine bouncing between these two different ways of writing it. It's just I'm pressing enter to get the other equal sign. And all we're asking you to do very quickly from here on out is just go from one form to the other. Identify the B, identify the E, identify the A, and write it in its other form. And that's all these other 5 examples are. So going in order, what this is saying is 3 is my base. The exponent, the other end of the log, is m. And I want to know, when do I get 27? How do I get an answer of 27? So if you can see it the other way, or we need to write this in a little bit, but uh-oh. Sorry about that. Someone found an old Christmas ornament and decided to play it. Anyways, we're gonna find another way to express what a log is saying. But for now, just tag along and use this identity, so to speak. So now these questions go the other way around. There is a base with an exponent and there's an answer. So can I rewrite this somehow? And the answer is yes. So this is now log. The base is 8, subscript 8. The answer is 4096, and the exponent goes on the other side of a log equation. Or in other words, a log determines the exponent that 8 was raised to get you this. Again, we'll rephrase that better in a minute. Let's look at this one and just, again, keep on using what we know. This is saying there's a log. Now, which one is the base here? Which one has an exponent? 3 has an exponent. I got 1 out of 27, and that's because the exponent was -3. All right, even faster, this would then be log base 5, gives me some answer when my exponent is 2. Catch that subtle wording, hopefully, that I'm using as I say these problems, because that helps. Now, before we do 6, this is another thing I warned you about, but let's see here. A square root is a fraction as an exponent. So a square root is a half exponent. And so now that I have a base, an exponent, and an answer, once I remember that about square roots, then I can write this as my base is 4. I want to get 2. And that's because my exponent was 1/2. Okay, so what I hope you take away from this is that we haven't actually done any math yet. Like, I did verify some stuff in your calculator, but we didn't actually solve anything. All we're doing here is just saying, can you rewrite it from form to form using some rewriting tools, and mainly this formula, how they go back and forth to one another. Okay, up next, now the question is when we dive into solving quote unquote without a calculator. Now, what I'm going to tell you is, by all means, just use your calculator. But I'm still going to approach these and show you how you could answer them without a calculator. And so really, maybe that's what we're going to do, is we're going to say, what is this saying actually? What is number 1 saying? It's saying 2 to what power results in, aka answer, so I know that's a bad way to write my quotes, but that's how I'm going to write it. But that's what this is saying. 2 to what power? I don't know the answers on the other side, or I don't know the exponent on the other side. So again, using this formula, like I see the 2, I don't have an equal something. So it's base 2 to which power gives me 32 is how you ask that. Now, that means you need to, without a calculator, literally you just have to write, I don't know, what's 2 to the first? 2 to the first is 2. What's 2 squared? 4. I'm still not at 32 yet, so let's keep going. What's 2 cubed? 8. What's 2 to the fourth? 16. What's 2 to the fifth? 32. And that's how you answer it without a calculator. It's not pretty, but the answer is 5. 2 to the 5th power gives you 32. And you can verify that again in your calculator. Is 2 to the 5th 32? Yes, it is. Now, the other way of verifying it, I'm going to say this out loud here. I'm not going to write it formally, but this is what I mean by you can't just use your calculator. Now, here's what I need you to know. These are not dividing one another. They are not dividing one another as they're written presently. However, you are allowed to just divide them. What do I mean by that? If I type just log, every calculator scientific has a log button. If I just type log 32, 32, and close the parentheses, and divide it by the log of that tiny number, or the base as we call it, 2, look at that, I get 5 as well. Now, this is technically called the change of base formula for reasons I can't tell you right now, and let's just keep on going, because the intent is, can you do this without a calculator? All right, so similarly, for this example, we're saying 5 to what power gives me 1 over 25? Now, hopefully, you can pause and think back to the very first page of this module that we did in 4.1, and you can think about your exponents and how you might get a 25, which is related to 5 in exponent terms, but get a 25 on the bottom. And hopefully, with time and practice, you learn that that must mean that the exponent you raised it to was -2. Now, once again, just to spoil it, can you do that in your calculator? Of course you can. Here's how. You type, now you got to type carefully, and every calculator is a little different. We're going to first type log of 1 over 25 and close that parentheses out. And then I'm going to divide that by the log of just that tiny, base. So just by log of 5. There we go. I get -2. So same thing there. Also, this calculator's fancy. It does have what we call a log base. So now it actually shows up where I can put the 5 here and the 1 over 25 like normal. But you just need to know that it's log of the thing to the right divided by the log of the base, and you're good to go. It says don't use your calculator. Hopefully, with time and practice, you can learn that, oh yeah, 5 to the -2 gives me its square on the bottom. 2 is the square, or, 25 is 5 squared, 5 to the second. But 25 on the bottom means I must have had a negative to transfer it to the bottom. Hopefully you memorize that, and if not, well, then you've got to rely on your calculator, even though it says not to use it, but that's fine. Okay, up next we've got some logarithmic identities. Now these should not sound surprising or should not look surprising, although they look crazy magical at the moment. But we need to talk about them in their exponent forms, and then you'll see, oh yeah, that was actually kind of obvious, or maybe hopefully obvious. Remember that if I rewrite this according to log is bay, or that, formula up top, this formula again, this identity that they can transfer back and forth from one another, then once we look at this, this isn't going to be surprising at all. This is saying b to the 0 power is 1. And that makes sense because a while ago we said anything to the 0 power is 1. So that's just what that formula looks like, or that fact looks like as a logarithm. If b is raised to the 0, then you get 1. Or if you got a result or an answer of 1, doesn't matter what your base was, you raised it to the 0 power. Okay, up next, what about this one? Why does this one make sense? This is saying b, their little base b is right here. The 1 is now over here, and then equals the b that was up here. So catch that. This little tiny subscript b is the base. The base got the exponent of 1, and it's set equal to the thing to the right of, but before the equal sign in the logarithm. And so, why does this one make sense? Because what is this saying? Anything to the first power is itself, is the way you read that. Okay, now this is where we finally need to write out the sentence of what a log is saying. And so let's do that. So if I write this, what is this saying? It's saying, sorry, I shouldn't have put the quotes there. I should put them here. In general, actually, why do I feel like I wrote this? Oh yeah, no, I did. I wrote it right here already. I don't know why I felt like I didn't, but I'm going to write it again for this one. 3 to what power gives me 27? That's what a log is saying, and that's how it asks or talks. Now, if you can say that wording, let me read this out loud to you and show you this. This is saying b to what power, essentially, gives you b to the kth power. Or maybe even to say it directly, b to the kth power gives you b to the kth power. And hopefully that sounds like, well, no duh. But the thing is, the equal sign's about to be hidden from you. And so really what you're saying is, oh, if I have b to the k, then what was b raised to? And the answer is k. So this is why when I took college algebra, my professor used to say, logs are exponents. And what did he mean by that? He's saying if you look at this structure, a log ends up being, or a log is, or logs are, the exponent of your base. That's what a log is asking or searching for. What was the exponent on your base? Well, if my base is b, and I got b to a power, then a log is literally saying, just tell me what that power was. If that clicks, if that makes sense, great. If it doesn't, then just kind of memorize the pattern of if I see a number, and then that number, it's probably just that last number. And that's not mathematical, um, but it works, so we're going to go with it. Similarly, hey, look, I see a number, then log b of that number, and then a final number, and look, it's still the final number. So these two I am just kind of say memorize. And with that being said, let's dive into these last examples for this section. Okay, so we're being asked to determine the exponent of 5 that gets me the square root of 5. Now first, let me just rewrite this. And hopefully you know where I'm going here. How am I going to rewrite this using an exponent rather than a square root? We've seen this once before already. And hopefully you know we're going to use a 1/2 exponent. So in other words, a log is saying 5 to what power gives me 5 to the 1/2 power, and hopefully that sounds redundant, and we're looking at this formula right here. I just needed to deal with the square root to see that I was, so the answer here is 1/2. What exponent is on 5? 1/2. Done. Okay, let's keep on going. Similar idea, but be careful how you write this, and this one's honestly pretty tricky, so here we go. Also, don't miss this. You can just use your calculator. Don't read your math lab homework and think that you can't. So we'll type this into the calculator and do this in person together, but this goes by quick. But I do need to do some rewriting. This is really an exponent of 1/2. Now catch this, but it's on the bottom. And so if I have an exponent of 1/2 on the bottom, is there another way to rewrite that? You bet there is. A negative exponent up top. So catch that. That is a very subtle exponent law rule. A 1/2 or a square root is a 1/2 as an exponent. Because it was on the bottom, it can be rewritten as a negative exponent up top. And so now when I read this question, what is it saying? What was 2 raised to give you 2 to the negative 1/2 power? The answer is negative 1/2. So it's a redundant sentence. I just needed to do some rewriting. Okay, let's show you that in the calculator directly. So what I'm saying is you are or should feel comfortable writing log of 1 divided by square root 2 divided by that base, which was just 2. And look, there's negative 1/2. All right, so nothing shocking there. Well, maybe something shocking, but the bigger point I'm making is you can just type it into your calculator. Would it be nice if you remember those exponent rules and rewrote it? Yes, but we're not going to rely on that or trust that that happens every time. Okay, let's go a little bit faster now. 3 to what power gives me 3 itself? Hopefully you might know this one, or it's literally one of our formulas. The answer is 1. 3 to what power gives me itself? Anything to the first power gives me itself. Okay, 6 to what power gives me 1? Anything to the 0 power gives me 1. Again, those rules from the formula sheet on the last section right to you. This one is now a breath of fresh air. If I have 3 and I want to know how does 3 become 3 to the 4th power, well, it's because I raised it to the 4th power. So I know maybe that's what I'm trying to say here is I know this feels so simple compared to these two, but these two should feel as easy as this one. You should say, I still see a 5. I just need to rewrite that square root. I still see a 2. I just need to rewrite that square root on the bottom. And then I'm just following this basic logic. Now, finally, this is the kind of ugly looking one, but there's still a 7, log 7, 18. And so the answer just ends up being the 18, the last number at the end. For that one, honestly, don't worry about why, just trust. Okay. Last but not least, we have some special logs. Now, why are these special? Because where's the little number on the bottom? So that's what makes them special. So it turns out that due to how frequently things show up in mathematics, um, we decided to create some special scenarios to lazily write less and say more. That's, again, I've said mathematicians are lazy through this whole course. And what I mean by that is we're going to find the most efficient way to write something if it happens all the time. So what I'm saying here is this has an implied base of 10. So if you just see regular log with no little subscript number, no little subscript 5, 2, b, x, or whatever, then your base is 10. Now, why does that make sense? Well, because you might not know it, but we use the base 10 number system. That's why we have decimals. The Greek word root decimal is literally deci, 10. So all of that idea there, that's why we count by tens and other things like that. We have our place values due to tens. So because of that, and we use it so much, we decided to just say, hey, if you ever just see log without a number on the bottom, just know that it was 10 on the bottom. Now then there's this one, we call this one ln. Now, maybe it's for like Latin or Greek reasons, but it's actually natural log. So like the letters are out of order in how we say it phonetically, but I think that's due to language in the past. We don't need to worry about that, but just know that ln is actually just a regular old log. And in fact, I'm going to write it this way cheekily, but this is log when e is your base. Now, e is a special number. E is essentially 2.71 blah, 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 blah. It goes on forever. And it's got magical properties that we can't discuss in this course because it would take a whole course in itself pretty much. But essentially, if you had a log and its base was e, instead of writing log base e, we're just actually going to say, never mind, I'm going to call this a whole new thing and I'm just going to call it ln. But ln essentially just means e is the implied base. The very last thing I'm trying to say there is that log and ln are not doing anything different from one another. It's just that log and ln have, or rather, ln is specifically when you have a log whose base is e, so we just write it differently, but it's not doing any other mathematical rules differently. It just has a different base. All right, now with that being said, this last section is then a put 2 and 2 together. And what I mean by that is now, can you use these 4 formulas knowing that if you just see log, 10's on the bottom, and if you see ln, e is on the bottom, and think through these 4 rules for these questions? Well, here we go. This says log, so I know there's an invisible 10 on the bottom. And the question is, how does a 10 get raised to some power and become 10 on the bottom? And I'll spoil it for you. When you raise 10 to the negative first. And we talked about that, and we've seen it before. Again, all the connections are being made now. Take a look at what a negative exponent does. 2 to the negative 1 just puts the 2 on the bottom. So 10 to the negative 1 is how I got a 10 on the bottom. And so look at the way I've then written this. I'm saying log, there is a 10 invisibly there because I didn't see a base. And I got 1/10, or I got 10 to the negative first. And there's my rewriting that gives me that basic rule. Sorry, I'm like shuffling all the pages, but it is tricky. There we go. Okay, with that being said, we're going to fly through the rest of these pretty quickly. 10 to what power gives me 10 to the 34th power? 34. It almost feels silly. Now, 10 raised to the log of base 10, because I don't see a number there, 23. That's that special formula that, again, we're not even going to worry about it. We're just going to memorize it. That must be 23, because there was the 10, the little 10, and then 23. And so those all canceled for magic reasons, and we just got 23. Up next, what is this question saying? It's saying ln of 1. Now, this honestly is the easiest one to just plug into your calculator, but also, what is it saying? It's saying e to what power gave you 1? And remember, anything to the 0 power gives you 1. So take your calculator. You might not know what e is, but it's there on your calculator. I can press the blue second button, and right here I get my e. I can raise it to the 0 power, and anything to the 0 power is 1. One more question. E to what power gives me e to the 21st power? Again, why am I saying e and pointing down here? Because I see ln, so I know there's a base of e. So it's saying ln means e is your base. And how did your base become e to the 21st power? And the answer is I raised it to the 21st power. So I hope in these 5 questions, if I now say the phrase logs are exponents, or logs determine the exponent, that it really, really makes sense. 10 had to be raised to the negative first to give me 1/10. 10 had to be raised to the 34th to give me 10 to the 34th. It should sound redundant once it clicks, and you should be saying, that's all I'm doing? And the answer is yes, for now, and I'll see you on the next videos.